It is a section 5.4, one-step methods, accuracy comparison. To compare accuracy of the one-step methods we have learned so far, we consider the motion of the spring mass system given in this equation. Here the M and kappa F0, mu, and C0 will be specified later. This right side is a periodic driving force of a frequency mu and scaled by the mass. And for this second order differential equation, we can find the analytic solution as in this equation. Here, omega is the angular frequency. It's the same as 2 pi times the frequency f. Okay, to solve the second order equation, we introduce y1 is same as y, and y2 is now minus y prime scaled by angular frequency. Then this equation can be written in this form. This is a system of first order differential equations, so that now along with the factorized formula, the algorithms can be used to solve the problem. We'll deal with the details in section 5.6. Okay. Here we specify the parameters. Mass is 1, F is 40, A is 1, and the angular frequency is 4, which means that the frequency is 1, in fact 2, so that 2 pi times F. Okay. And here, now mu, that is for driving force, that's 2 pi. Okay. Okay, so from that setting, the fundamental period of the motion is 1. That means that, and here, that will make twice notation, but it will go to the original position in after 2 rotations, so that now in 1 second, I have to make 2 rotations and go to the original position. Okay, here, now that is the trajectory. Start from here, and that is y1, y value, so that in practice is moving, that's up direction, is down direction, up and down, so they go down and go up here and go down and go up this position at time 1. But here y2, that is here the derivative value and minus derivative and scaled by omega, so that in pictorial purpose it is given in this way, and also for the computation we introduced the y2, and here picture is given, so that along with y1 and y2 coordinates, it is turning that way and turning, and here going to that. So the fundamental period is 1, but now 2 rotations, right? Okay, we have accuracy comparison, Euler method with HS 100, 200, 400, 800. The error is given in this way. So you can see that it's first order. For longitudinal second order, you can see better accuracy, and now that is really second order by comparing the accuracy error. Here we can find the accuracy order. For fourth order longitudinal method is way better than other two. Here error is really small. Here the error is measured at the terminal point, and so that in L2 norm, and the measure, in fact, the distance is measured by using this L2 norm at the last moment. And by using the error, these are known, this value and that value, and here logarithm divided by logarithm 2 is the order of convergence alpha. So these values are alpha values, and we can see quite easily the algorithms are working and as expected. Okay, here now okay, so RK4 shows a much better accuracy than the lower the methods, which explains the popularity of the method. Okay, here finally we'll consider how to get, why we get the order of convergence in this way. Okay, here and if we assume that in the beginning the algorithm has an error in order alpha, then we may write down in this way, this is quantity after measuring the error with the computation done with h, then there is a c times h to the alpha. If you try to get another error along with ph, p can be half or p can be 2, and you can measure the error after simulation. Then from the assumption, it must be following this quantity. So we have to solve the problem for alpha. In order to do that, we just measure the ratio. Then here we have this term and that term. And now everything else will disappear except p to the alpha. C can be cancelled. H to the alpha must be cancelled, and p to the alpha is remained. Now, we already know this value and that value, and also p is known. That is from your choice, so that we can solve for alpha. In order to do that, you're applying natural logarithm. Then natural logarithm of this one is same as, now the power can go out by using power rule, alpha times logarithm p. By dividing the terms by logarithm p, we can reach at this solution. So that is exactly when p is 2, that term. Okay? Okay, that's the end of the section. Thank you.